Now that we've had our introduction to polar coordinates, let's start referring to polar functions. Now, as far as Cartesian functions were concerned, usually the two different forms that we had for Cartesian functions were when y is a function of x or x is a function of y. So y equals f of x or x equals g of y. For polar functions, the two variables that we're working with are r and theta. And most typically, the kind of function that you're going to see is that r is going to be a function of theta. And typically, we don't see it the other way around because theta usually involves something along the lines of a sine of theta or a cosine of theta. So theta isn't necessarily unique while r is unique. So an example of a polar function would be something along the lines of r is equal to 6 times the cosine of theta. Now, I wanted to do a couple things with this, mostly talking about how to graph an object like this. And there are two methods for graphing something, which is leave it in polar coordinates or convert it into Cartesian coordinates. So if we leave it in polar coordinates, then our goal is going to try to be to get x as a function of only one variable and y as a function of only one variable, and then we can take care of this thing parametrically. So x would be equal to r times the cosine of theta, which is one of the conversions from the last section, and y would be r times the sine of theta. However, we know what r is equal to, so what I'm going to do is make a substitution on r and call this 6 times the cosine of theta times the cosine of theta, which of course simplifies into 6 times the cosine squared of theta. For the y-coordinate, that would be 6 times the cosine of theta times the sine of theta, and there's no additional algebra to do with that. So if I wanted to graph this thing in polar coordinates, I could pick several different values of theta, plug them in, and calculate the corresponding values of x and y. So with that in mind, I am going to pick the following values. Theta equals 0, pi over 4, pi over 2, 3 pi over 4, and pi. That'll just be for the time being. Now plugging each of these into the given things, the cosine of 0 would be equal to 1, so this would be 6 times 1 squared, or 6. For the y-coordinate, that would be 6 times cosine of 0 times the sine of 0, which would be 0. So first ordered pair that we would see on this graph is going to be 1, 2, 3, 4, 5, 6. 6, 0. Then, as theta starts to increase at pi over 4, this would be 6 times the cosine of pi over 4, which is root 2 over 2. If you simplify this completely, you're going to wind up getting 3. For the y-coordinate, this would be 6 times cosine of pi over 4, which is root 2 over 2, times the sine of pi over 4, which is root 2 over 2. And again, if you simplify this as much as possible, you will get 3. So a second ordered pair on here would be up here at 3, 3. At pi over 2, we would be looking at 6 times 0 squared. Cosine of pi over 2 is 0. And then 6 times the cosine of pi over 2 times the sine of pi over 2, which would be equal to 0 as well, taking us to the origin. At 3 pi over 4, we're now going to see that the cosine is going to wind up being negative, so this will be negative root 2 over 2. We're still squaring it though, so we're going to wind up getting positive 3. For y, we'll get 6 times the negative root 2 over 2, and the sine of 3 pi over 4 is positive root 2 over 2, which will give us a running total of negative 3. So x-coordinate is positive 3, y-coordinate is negative 3. And finally, up to pi, this would be 6 times cosine of pi is negative 1. Square it and we get 6. And for the sine, that would be 6 times cosine of pi times the sine of pi, which takes us back to 0, telling us that we're going to finish up right here. So that only gives us a little bit of a structure as far as what this thing looks like. If we wanted to figure out better what this thing looks like, the alternative would be to convert to Cartesian equation. So as a Cartesian equation, we would have r is equal to 6 times the cosine of theta Now we do have a conversion if we have r times the cosine of theta, so what I'm going to do is start by multiplying both sides by r. Left-hand side becomes r squared, right-hand side becomes 6 times r times the cosine of theta. We now have a conversion for r squared into Cartesian. That would be x squared plus y squared. And r times the cosine of theta would become x. 6 would stay as 6. Now at this point you probably recognize that this thing is a circle due to the x squared plus y squared, but it's not in the appropriate standard form of a circle. So what we're going to do is bring the 6x over to the left-hand side and we'll complete the square. Divide the negative 6 by 2 and square the result. That gives us 9. 9 will complete the square. And so we'll add 9 to both sides to complete the square. This lets me know that in standard form, this circle would be x minus 3, quantity squared, plus y squared is equal to 9. Hopefully this is recognizable as a circle with a center at 3, 0, and a radius that is equal to the square root of the right-hand side. That would be a radius of 3. Now taking a look at the graph that we came up with back here, hopefully it is now believable that this thing would be a circle of radius 3 with its center at 3, 0. You'll notice though that we didn't have to go through the entire 0 to 2 pi to sweep this thing out. We started at theta equals 0 pointing us in this direction and continued to sweep out the points that were associated with this. You'll notice that as soon as we got over to 3 pi over 4, the value of r became negative, and when we got to pi, the value of r was still negative, which instead of pointing us into quadrant 2, pointed us into quadrant 4, and then eventually back to the positive x-axis. So, just one example of a polar graph.